Greetings, gentlemen, and the 3.5 ladies who watch this channel. Yesterday, I was bored. And math nerds are not supposed to be bored because when we're bored, terrible things happen. I would love to expand on the nature of those things, but my lawyer advises against it, so I'm gonna only mention the details that are probably not gonna be used against me in a court of law. I was playing around with this integral. The seemingly harmless integral I defined as the integral from 0 to pi by 4 of root cotangent x minus tangent x dx. Yes, it's not a glamorous integral at all, but you can solve it two different ways. And connecting those two different ways yields another insanely cool calculus result that, although seems completely unrelated to the integral, is actually very closely connected to it. So first, let's solve this integral to actually figure out what it evaluates to. And for that, I'd like to expand the cotangent and the tangent functions. So that way we have the integral from 0 to pi by 4 of cosine x divided by sine x minus sine x divided by cosine x dx. This equals the integral from 0 to pi by 4 of root cosine square x minus sine square x divided by sine x times cosine x dx. Now, if I pop in a factor of root 2, then notice in the denominator, we do indeed have sine 2x, and in the numerator, we do indeed have cosine 2x. So we have root 2 times integral 0 to pi by 4 root cosine 2x divided by sine 2x dx. And this, of course, is the square root of tangent 2x. So I have integral 0 to pi by 4 of root tangent 2x dx. Now for a nice substitution, we're going to let we're going to let 2x here equal theta. And this implies that dx equals 1/2 of d theta. Yeah, that should work. And this implies the target integral I equals root 2 times the integral from, well, as x approaches 0, theta will approach 0 as well. And as x approaches pi by 4, we have theta approaching pi by 2. And of course, we have this factor of 1/2 outside. And that means we're left with tangent theta d theta. And expanding the tangent function once more, we have outside 1 by root 2 times the integral from 0 to pi by 2 of sine to the 1/2 of theta times cosine to the negative 1/2 of theta d theta. And now we can invoke the beta function. So the beta function with complex arguments u and v is defined as twice the integral from 0 to pi by 2 of sine to the 2u minus 1 of theta times cosine to the 2v minus 1 of theta d theta. So on comparing the exponents, we have 2u minus 1 equal to, much better, equal to 1/2, and this implies that u equals, okay, I'm not very good at math, but I think this is 3/4. Yeah, and we have 2v minus 1 equal to negative 1/2, which implies that v here equals 1/4. Okay, cool. So this implies that the target integral I is actually 1 by root 2 times 1/2 the beta function evaluated at 3/4 and 1/4. And we know the relationship between the beta and the gamma functions. So we have beta u and v equal to gamma u times gamma v, terribly sorry about that, divided by gamma u plus v. And this implies that the target integral I equals 1 by 2 root 2 times gamma 3/4 times gamma 1/4 divided by gamma 3/4 plus 1/4, which is 1, and gamma 1 is itself equal to 1. So we can write this as 1 by 2 root 2 gamma 1/4 times gamma 3/4 is 1 minus 1/4. And now we can employ Euler's beautiful reflection formula, whereby we know that gamma z times gamma 1 minus z equals pi times the cosecant of pi times z. And z here is just equal to a quarter. So I here equals 1 by 2 root 2 times pi times the cosecant of pi by 4. And pi by 4 is, of course, root 2. So this implies that I here equals pi by 2. Okay, cool. But what about that really cool calculus result I was talking to at the beginning of the video? Well, for that, we're going to have to transform the integral slightly. And by slightly, I mean drastically. So we'll start off with letting tangent theta here equal x squared. And this implies that secant square theta d theta equals 2x dx. But this means that d theta is 2x dx divided by secant square theta. Now, secant square theta is just 1 plus tangent square theta, and tangent theta is x squared. So d theta transforms into 2x dx divided by 1 plus x to the 4th power. Okay, cool. So that's the differential element. This is how the variables are related. Now, what about the limits? Well, as theta approaches 0, x will approach 0 as well. And as theta approaches pi by 4, tangent theta approaches 1, so that means x approaches 1. Okay, cool. So that means the target integral I is now an integral from 0 to 1. We have this factor of 2 outside because of the differential element. We have root, cotangent is 1 by tangent, so we have 1 by x squared minus x squared times 2x divided by 1 plus x to the 4th power dx. So that means we have, oh wait, I already put the factor of 2 outside. So we have twice the integral from 0 to 1 of, let's see, we have 1 minus x to the 4th power in the square root divided by x. And we have x up top and 1 plus x to the 4th power over here. Some cancellation takes place. And this implies that the target integral I, which we know is equal to pi by 2, equals twice the integral from 0 to 1. Of root 1 minus x to the 4th power divided by 1 plus x to the 4th power dx. But what on earth do we plan to do with this new version of the target integral? Well, we do know that we can expand 1 by 1 plus x as the geometric series, that is the sum over the non-negative integers k of negative 1 to the k times x to the k, as long as the absolute value of x is less than 1. And this is valid for both x and x to the 4th power on our interval of integration. So this implies that 1 by 1 plus x to the 4th power equals the sum over k of negative 1 to the k times x to the 4k. And that means we can write the target integral I as twice the integral from 0 to 1 of root 1 minus x to the 4th power times the sum over k of negative 1 to the k times x to the 4 times k dx. We can take this thing inside the summation operator because it's independent of the index variable k, so that we have twice the integral from 0 to 1 of the sum over k of negative 1 to the k times x to the 4 times k times root 1 minus x to the 4th power dx. And we know that this thing converges, so we can switch up the order of the integration and summation operators so that we have twice the sum over k of, wait, this should be a sum starting at 0, terribly sorry about that, of negative 1 to the k times the integral from 0 to 1 of x to the 4 times k times 1 minus x to the 4th power to the 1/2 dx. All we need now is the obvious substitution, that is letting x here equal u to a quarter, which implies that dx equals a quarter of u to the negative 3/4 du. And the limits of integration are clearly not bothered, so we have I here equal to twice the sum over k of negative 1 to the k times the integral from 0 to 1 of u to the k times 1 minus u to the 1/2 times u to the negative 3/4 divided by 4 du. And of course, this can be simplified to I being equal to 2 divided by 4 is 1/2. So we have 1/2 the sum over k of negative 1 to the k times the integral from 0 to 1 of u to the k minus 3/4 times 1 minus u to the 1/2 du. And now it's time to employ the beta function again, but a different integral form of the beta function. In this case, we recall that the beta function with complex arguments x and y, because I'm already using u as a variable of integration, this here equals the integral from 0 to 1 of u to the x minus 1 times 1 minus u to the y minus 1 du. So on comparing the exponents, we do indeed have x minus 1 equal to k minus 3/4, which implies that x equals k plus 1/4, and we have y minus 1 equal to 1/2, which implies the y here equals, well, 3/2. Okay, cool. That was interesting. So now we have a sum of beta functions, which is absolutely insane. So we have I here equal to 1/2 the sum over k of negative 1 to the k times beta k plus 1/4 and 3/2. And now, of course, we plan to apply the relationship between the beta and the gamma function. So we have 1/2 the sum over k of negative 1 to the k times gamma k plus 1/4 times gamma 3/2 divided by gamma k plus 1/4 plus 3/2. So what exactly was gamma 3/2? Gamma 3/2 is just gamma 1 plus 1/2, so that's 1/2 times gamma 1/2. That means it's just root pi by 2. So we have root pi by 4 outside times the sum over k of negative 1 to the k times gamma k plus 1/4. Terribly sorry about that. That looks more like the golden ratio, whatever. So we have k plus 1/4 divided by gamma k plus, okay, this is the hard bit, 1/4 plus 3/2. What is that? My math is not so good. I think this is, yeah, that should be 7/4. And this is the sum that we have on the left-hand side and on the right-hand side. And on the left, we have I, which we know to be equal to pi by 2. So this is absolutely awesome because we can expand by 4 divided by root pi, which implies that the sum over k of negative 1 to the k, terribly sorry about that, negative 1 to the k times gamma k plus 1/4 divided by gamma k plus 7/4 equals what exactly? We have root pi times 2. We have 2 times root pi. Do you have any idea how insane this looks? We have a sum, an infinite series of ratios of gamma functions, and this so nicely sorts out to, it so nicely converges to something involving pi, root pi specifically. This is awesome. I mean, this is beautiful. I hope I did not mess up any of the arithmetic along the way, but this is still amazing. This is just gorgeous, man. I mean, I really enjoyed this solution development, and I'm really glad I was bored yesterday and I was forced to just play around with a relatively simple integral, very simple rather, relative to the other stuff I do here on the channel. But that was fun. I hope you enjoyed the video as well. Be sure to like and subscribe and share the video as well. Share it to your friends, family, fellow cult members, whatever. I'm sure they're gonna enjoy this as well. Be sure to like and subscribe. Do drop me a follow on Instagram, and in case you like the content, you can support me on Patreon. Thank you. See you next time.